Okay, so we are working our way through this activity 6, and we have one more example of using this equation. And it's, what is the concentration of A after 30 seconds if the initial concentration of A is 0.6 molar? So remember that from before. So this is ln of 0.6 molar, which we figured out is minus 0.511 minus 0.0320 now times 30 seconds, okay? So if you multiply out that, you get 0.960. So now you're basically adding these two negative numbers. You get minus 1.471. So this is the natural log of the concentration that we want. So we will have to take the inverse natural log of negative 1.471 or e to the minus 1.471. Either way, you're going to get 0.230 molar as the answer. So if we want to know how much the concentration of A changed between 20 and 30 seconds, it went from 0.316 molar at 20 seconds to 0.230 at 30 seconds. You take the difference, comes out to 0.086. So this is the change in concentration of A in the third 10-second range. Because if you remember, we did 0 to 10, 10 to 20, and now 20 to 30. And the change in concentration, let's see, we found that it was 0.164 in the first 10 seconds. It was 0.120 in the second 10 seconds, and now it's only 0.086. So what you can see is that the reaction is certainly slowing down as we expected. All right, so putting that together, let's see, at 10 seconds, so initially the concentration was 0.6 molar. After 10 seconds, the concentration was 0.436 molar. After 20 seconds, it was 0.316 molar. And after 30 seconds, 0.230 molar. So I'm going to talk a little bit about something called the half-life. And what this D asks you to do is estimate the half-life. Now, what is the half-life? The half-life is the time it takes for the concentration of the reactant to decay, in other words, to go down, decrease, to half of its initial value. So we started at 0.6. The half-life, which we often call T1 half, would be the time it takes for the concentration to get to 0.3. Okay, so you notice here that, let's get these colors back, that 0.3 is somewhere between 0.23 and 0.316, closer to the 20 seconds. So I would say that it takes a little more than 20 seconds to get from 0.6 to 0.3. Okay, so I would estimate that the half-life is a little greater, a bit larger than 20 seconds. Okay. All right, so now I'm gonna skip a little bit. I'm gonna talk about some other stuff related to this, and then I'll come back to what the half-life actually is, So what I'm going to do is take a closer look. So it's time for a closer look at this equation. The equation that we've been working on for a while. So if we were able to take data for how the concentration changes during a chemical reaction, and if that reaction was first order, so that if we were able to take data for how concentration changes over time for a first order reaction, because remember, this equation is only valid for a first order reaction. So if we were able to take data, suppose we had data for how the concentration changes over time for a first order reaction. And how would we get this data? So one way we could get it is a lot of times we could use the fact that concentration and absorbance are proportional to each other. So we could, for example, monitor the absorbance with time. And in fact, I showed you data for this on the very first day we studied this when we were talking about the crystal violet reaction. That if I took a sample of that crystal violet as that purple color was fading, okay, over time, the color fades. And as the color fades, the chemical that's doing the absorbing is actually decreasing in concentration. And so it would absorb less and less as it had a smaller and smaller concentration. So one way I could get data for how concentration changes over time is I could look at how absorbance changes over time. And if the reaction was first order, it would have to obey this equation. The log of the concentration, let's say, of A, the reactant, is the log of A0 minus KT. So if this is the equation that represents how the concentration changes over time, then it tells us what we can do to actually figure out if the reaction is first order. Like suppose we didn't know the reaction was first order. How could we figure out if the reaction really is first order? So how could we figure out if the reaction is first order? I don't know what's going on here. I probably have too many windows open or something. Okay, and what we could do is if you take a close look at this equation, you see now, and let's not forget that what we will have is we will have data for the concentration of A versus T. So we'll have this concentration of A and time. So we'll have all kinds of numbers here. Okay, and if we did a graph of the concentration of A versus time, we know that graph would not be a line. This would not be linear. But if we take a close look, as I've been promising for a while now, at this equation, if you actually graphed, instead of the concentration of A, the natural log of A versus time, okay? So if you put this on the y-axis, so you put this on the y-axis and put time on the x-axis, we see that there is this linear relationship between the log of A and time, okay? Because the log of A0 is just a constant. It's just the log of the initial concentration. Like in the example we spent a long time on, this would be the log of 0.6. That's just a number, right? That's minus 0.511. That is not changing. So that's a constant. And also, of course, the rate constant is a constant as long as we don't change the temperature, okay? So if we graphed the log of A versus T, well, we would see a line. And the line would look like that. And from this equation, you could see the log of A is the log of A0 minus KT, that the slope, okay, so if this is what's plotted on the x-axis, and this is what's plotted on the y-axis, then the slope is minus k, because remember we have y equals b plus mx, and so that slope is the negative of the rate constant, and the intercept is the natural log of the initial concentration. So this guy here is actually the log of A0. So that's the maximum value that the log of A will have, is its initial value when A is at its maximum concentration. And then over time, this will go down in a linear fashion. And the slope is minus k. Okay, so the greater the rate constant, the steeper this slope is going to be. This is what's going to happen if k is greater. You know, it would be steeper for a larger k. So you would have a much more precipitous drop in the concentration of A, or the log of the concentration over time. So what's the big conclusion here? Okay, so the big conclusion is that if we plot the log of the concentration of a reactant over time, and we get a linear plot, then it means the reaction was first order. So we have a method of figuring out if that reaction is first order. Now, this is not the only method that we know to figure out if a reaction is first order, because what else could we do? How could you figure out if a reaction is first order? So there's another way that we learned, right? We learned that if you say double the concentration and the reaction is first order, that will double the rate. If you double the concentration of a reactant and the rate, quadruples, then the reaction is second order. So one way to determine if a reaction is first order is to double the concentration of that reactant, leaving anything else constant, and seeing what happens to the rate. And if it doubles, then the reaction is first order. So the other way is to say double the initial rate, the initial concentration. You can't double the rate, you have to double the concentration of reactant. If the rate, which we usually measure the initial rate, doubles, that means the reaction is first order. So that's one way to get to figure out if a reaction is first order. So that's one way. The other way is you plot the log of that concentration versus time. If you have a linear graph, it means the reaction is first order. And you also get the added bonus that the rate constant is the negative of the slope. So that's a very nice thing to know, to be able to use. So let me talk a little bit about half-life, because I gave you a little introduction to what it means, but we can actually use the equation that we know for first order reactions to figure out the half-life. And so we're going to get a formula for it for a first order reaction. Okay, so remember what the half-life is. This is the time it takes for the concentration of a reactant to decrease.